So I've been giving talks for like 10 years now, but I still get nervous as a speaker. So if speaking is something you're wanting to get into and you're nervous about it, don't worry about it. I think everyone's still nervous. But it's something I let myself get carried away with sort of imagining, well, almost fantasizing about the worst things that could happen to me on stage, just so I could feel prepared for it. And I've done the numbers, I've gone through all of them, and I think I've figured out what the worst thing that could possibly happen is. Is anyone can we suggest something really bad that could happen to me in the next 45 minutes? Fall off stage is a good one, yes, particularly here because, it's very narrow here, it ends there, so there's a good chance that would happen. That would be a terrible thing because it would be my fault, so there's a high level of embarrassment, and also, like, if I did just take a tumble off here, then, so there'll be gasp of horror, I understand that, but there'd be a good percentage of you who would be laughing, right? Because humans falling over, that's funny. Any other suggestions? Heart attack. Interesting one. Yeah, okay. So do you know what? I don't include like passing out or a heart attack is not really high up my list because like it would happen. There might be a moment where some people are thinking it's part of the act or that I'm trying to make a point. But for me, the kind of embarrassment level would be fairly minimal. I would be busy having a heart attack, right? It's fine. And also, everyone would know what was going on straight away. I did a meetup talk where I asked people the same question, what's the worst thing? And someone shouted out, hit by a bus! Okay, I mean, once again, like the potential for embarrassment is quite low because I wouldn't see it coming, right? I don't think any of us would expect it, and it would just be like, oh, bus, and then it's over, right? Like I'm dead, no embarrassment. No, I've ran the numbers, I've imagined everything, and the worst thing that could possibly happen to me in the next 40 minutes is if I shit myself, and I don't mean like an explosive shit myself, where we all know what's going on. It would be something that initially only I would be aware of. Like, I'd be like, and then if this piece of code, and then it's like, well, what do I do, right? Because if at that point I just go, sorry, and walk off the stage, and everyone's like, well, why did he just stop his talk? Like, we've paid money to, see speakers. It's a bit cheeky just walking off halfway through. So the only choice I would have is to just continue and sort of squelch my way through the stage, try not to make it noticeable. But the smell would drift, right? And I would see that happen, and I would see someone in the front row go, and that's it. And I would just have that horrible thing where I could just see row after row slowly come to terms with the fact that I shot myself on stage. I'm really hoping that isn't going to happen. It's the worst, but I am prepared for it. I fought through it all. But it's something I stress about because I stress a lot. I stress about code like this for a number of reasons. Firstly, because there's no semicolons. Give me a cheer if you use semicolons in JavaScript. You're the good ones. The rest of you are monsters. But that's not the real reason this stresses me out. It's because it's adding something to the DOM, right? And then hiding it, presumably to show it sometime later, like on a click or something like that. But can we be sure that the user is not going to see a flash of that element before it's properly hidden? I mean, I've never seen this happen. I've never seen it happen before. But, race conditions, it's one of those things. Can we be sure that this is never going to happen? I don't know. So with code like this, I would always just swap it around. And, that would keep me calm. I'd be able to sleep properly that night. But in reality, there is no race condition here. The timing of running code versus rendering is all tightly defined and mostly deterministic. And that is thanks to this, the event loop. And if I do a half-decent job in the next 30 minutes or so, you'll know why things run in the order they do. And I don't know, it might even make sense, but no promises there. So web pages have this thing called the main thread. This is the main thread. It's called the main thread because lots of stuff happens there. It's where JavaScript happens, it's where rendering happens, It's where the DOM lives. And it's good, because it means the bulk of stuff on your page has this deterministic order. And you don't get multiple pieces of code running at the same time, modifying the same DOM and ending up with weird race conditions. But it does mean that if something on this main thread takes a long time, and by a long time I mean 200 milliseconds, that's a long time for a processor, it's really noticeable because it blocks other stuff from happening, blocks rendering, blocks interaction. And I think it's difficult for us to think in this way because as human beings we're extremely multi-threaded by nature. I can stand here, I can wave one hand, I can stand on one leg, I can wave the other leg, and all the time I'm sort of talking, I'm breathing, I'm processing visual and audio information. As humans, we don't have this main thread thing. We don't have things that block unrelated things, except for when we sneeze. Because as you begin to sneeze, your whole body just shuts down, right? You lose the ability to talk. That comes first. You pull a stupid face. It's the second thing that happens. If you're driving at this point during a sneeze, this is the moment you get to think, I hope I survive this. Hope no one dies as a result of this. So the human body becomes entirely single-threaded in this moment. You are sneezing, nothing else. You can't see, you can't hear, you can't think. You can move and make noises, yes, but only in ways that the sneeze wants you to. You have no control over what's going on. And then it's over, right? You essentially kind of wake up out of the sneeze, and that's when you find out if your car is still on the road, if you have the same number of limbs that you started with, the same number of passengers that you started with. But needless to say, we don't want code that runs like a sneeze. So although there's this main thread, we tend to spawn a whole series of other threads for networking stuff, for encoding, for decoding, for crypto, for monitoring input devices. But once these threads have done something, and they've got something interesting out of it that the page needs to hear about, they need to get their information back onto the main thread. And it's the event loop that orchestrates all of this. Take set timeout, for instance. I think it's a badly named function. I think the arguments are the wrong way around, but it's something we can use to schedule work sometime in the future. But have you thought about how it actually works? So I do a lot of web standards work at the moment, so let's write a simple web standard for set timeout. So here we go. The set timeout method, when invoked, must run the following steps. 1, wait ms milliseconds. 2, invoke callback. Done. But this isn't quite right, because spec text runs on the same thread as whatever starts it, whatever starts this work, and in this case it would be JavaScript. So when we say something like wait 5,000 milliseconds, it's going to be doing that wait on the same thread where it started, so it's going to be blocking that main thread for 5 seconds. This spec is very sneezy, it doesn't really work for what we're trying to do. So instead we do this magic piece of spec text, we say run the following steps in parallel, and that is just a convention we have for saying whatever thread you're on, get off it, do the following steps somewhere else. But we've created a problem here, because in step 1.2, we're saying invoke callback. We're trying to call JavaScript from a thread other than the JavaScript thread. So, and that doesn't make sense, because else we'd be calling callbacks in multiple threads. There's no sort of scheduling implied here. It doesn't really work. It'd be horrible race conditions. So we do this, another piece of spec text. We queue a task to run the following steps. And this is just a way of saying, hey, wait for a good chance to get back onto the main thread and then do the rest of these steps. And that ensures we're calling JavaScript on the thread where JavaScript lives and everything has a deterministic order. And this is a core part of how the browser works. How does a click event get from the operating system into your JavaScript? It queues a task. If you fetch something, how do you get hold of the response from the networking layer? It queues a task. If you're sending a message from the page to a web worker, how does that data get across? It queues a task. So the first part of the event loop, we're going to have a look at are task queues. And this is kind of some of the oldest part of the event loop. This is something that's existed in browsers for a very long time. And rather than dive into the spec, I'm going to try and visualize it. So here it is. This is the event loop. Hope that clears up any questions you had. I actually really hope it does, because the whole talk is based around this diagram, so I really hope it works. Without anything to do, this is what happens. It just sort of whizzes round and round in a CPU-efficient manner. This visualization is running at a fraction of 1% of real time, and it's still really too fast to see what's going on, so we'll slow things down. Makes it easier to see what's going on. So when we queue a task, the event loop takes a detour. So there on the left there, this is where tasks happen. So at some point, the browser says to the event loop, I've got a job for you. And the browser's like, fine, I'll queue that up, and I'll deal with it at the next opportunity I have. Fine. But what if we had two callbacks like this? We had two set timeouts, and they're going to call those two callbacks after 1,000 milliseconds, so 1 second. According to our spec, these two algorithms are going to go parallel. They're going to hang around in parallel space for 1,000 milliseconds, and then they each queue a task to do something back on the main thread. So in this case, the browser says to the event loop, I've got something here that wants to do main thread work. Oh, actually, I have two things that want to do main thread work. And the event loop's like, sure, that's fine. Add them to my to-do list, and I'll execute them in the order that you gave them to me. And that's it, no problem. Does one, goes around the event loop, and does the second one. And there's actually more than one task queue as well. You were showing one queue there, but specs can define lots of different queues. So here we've got two task queues, each with 3 items in them. The event loop gets to pick whichever task queue it wants each time round. And this allows it to prioritize things like input-related tasks over maybe things like network tasks that might be less important at a given moment. It guarantees that things inside each queue are going to be executed in the order that they were added, but it doesn't guarantee which queue it's going to take items from. So that's tasks. That's it. And it'd be pretty simple on their own, but we're going to take a look at the render steps as well. And this is what the browser uses to update stuff on the screen. So the render steps, this is another detour. We're over here this time. It involves computing styles. So that's figuring out which styles apply to which elements. You've written all your CSS, all the cascading's happening. The browser just wants to link each of those to a particular element on the page. And then it's creating a render tree, performing layout. And this is really just taking the elements that are going to be rendered and figuring out where they would go on the page. So they're kind of the X and Y position and their width and height. And then actually creating pixel data for those things, the actual painting. So with this going on, at some point the browser will say to the event loop, hey, actually interested in doing something to do with updating the screen, and it takes that detour and does the style calculation, the layout, and the paint. So when I'm writing code, something I often do by accident is get my JavaScript into an infinite loop. And it's something that different browsers handle slightly differently, but I'm going to take a look at what Chrome does in this situation. So here I've got a page, got text, got a GIF, got a button here that's going to run an infinite loop. Once I press that button, the tab locks up. I can't select text anymore. The GIF animation has stopped. So the code here is pretty simple. It's just this. That link is clicked, and we're just going to run a while loop like that. So we can show what is going on here in terms of the event loop. So the user clicks a button, and that queues a task to run the event listener callback. And it gets around to there, but this is where the infinite loop happens. The event loop's like, yeah, cool, I'll do this task, no problem. But this task never ends. It's running JavaScript forever. A couple of milliseconds later, the browser says, hey, event loop, we need to update that GIF, so could you render at your next earliest convenience? And the event loop's like, yeah, right, okay, no problem, I'll get round to that right after I'm done with this infinite loop. And then the user tries to highlight text, and that involves like hit testing to figure out which DOM elements are being clicked, like which text is being highlighted, lots of reading and writing. So the browser says, I've got a couple more items for that to-do list of yours to the event loop. And the event loop's like, mate, are you taking the piss? Do you know how long it takes me to do an infinite loop? There is a little bit of a clue in the name. It's going to take me a long time. So this is why an infinite loop like that, it blocks both rendering and interaction. And this is actually a good thing in practice. Like, going back to the code that I showed earlier, I was sort of worried, like, is there a non-deterministic order? Could something happen that has this element show on the page before we actually hide it? But no, like, this JavaScript is going to run as part of a task, and it has to run to completion before it can get round to the render steps. So it will be appended, and it will be hidden, and rendering cannot happen in between. Still stresses me out. I will still swap those lines around. So a while loop blocks rendering. But what about this? So this is a function that calls itself but using set timeout. So it's an infinite loop again, but using tasks for each item. So here's a screen cap of it. Click the button, GIF's still going. I can still select text. Kind of looks like nothing's really happened. Still interact with the page. So going back to the diagram, what's happening here? Click the button and it queues a task, and in that task, it queues a task, and round it goes. So it's no problem. Like, if the browser does actually want to render, because it's having to go all the way around this loop to process the next item, it can't stop and do two tasks. No, it has to go all the way around. So if the browser thinks at some point, hey, I'm going to update stuff on the page, that GIF, it can take a detour around the render steps. So this is why that kind of set timeout infinite loop doesn't block rendering. But if you want to run code that has something to do with rendering, a task is really the wrong place to do it. Like, tasks are on the other side of the world to rendering as far as the event loop is concerned. We want to run code that is within these render steps themselves, about here. And this is where the browser actually lets us run code. It's called request animation frame. You might have heard of it before. It's another badly named function, I think. Request animation frame callbacks, they always happen as part of the render steps. They're always part of that sequence of events. So to show why it's useful, I'm going to animate this box. It's just a box. Here's the code. Nothing special, really. I'm going to move the box forward 1 pixel, and then request animation frame to loop back around and move the box forward 1 pixel again, and on and on. And that's it. No problem. That's request animation frame. But if I did exactly the same thing, but instead of using request animation frame, let's say I used set timeout instead and use a timeout of 0 there. It looks like this. So roughly the same, but this box is moving faster. In fact, it's moving around about 3.5 times faster, I'd say. And that means the callback is being called more often than it is in our request animation frame example. And that's not a good thing. It's not a good thing at all. We saw earlier that rendering can happen between tasks, fine, but just because it can doesn't mean it must. You know, the browser might say, oh, do we need to update the GIF this time around? Nah, let's not. Let's pick another task. We'll do another one of those. Should we render this time? No, actually, I fancy doing another task first. Fair enough. And at some point later, the browser will go, okay, yeah, this time we'll do another animation frame. The browser gets to decide when to render, and it tries to be as efficient as possible when it does this. The render steps only happen if there's something to update. So if nothing's changed, it won't bother. If the tab is in the background, if it's hidden, it won't bother. But also the majority of screens, they update at a set frequency. In the case of this screen and most screens, it's 60 times a second, but some screens will run faster or slower. 60 hertz is the most common. So if we change page styles like 1,000 times a second, it won't render 1,000 times a second. It will synchronize itself to the display and only update 60 frames a second, 60 times a second. And that's good, right? Because otherwise it would be a waste of time. It would be using CPU it doesn't have to be used. There's no point rendering things the user will never see. But that's what set timeout is doing here. The box is moving faster because it's updating the position of that box more times than the user will see, more times than this display is capable of showing us. Okay, so far we've been using set timeout as a kind of proxy for saying queue a task. But even if we say 0 milliseconds here for set timeout, it's not really what the browser does. It's actually more like 4.7 milliseconds. The spec just says the browser can wait any amount of time it wants here, but most browsers seem to settle on 4.7 seconds for whatever reason. There isn't really a simple method that just queues a task. It's something you can kind of fake using message ports. We can sort of emulate it. And that just queues a task and nothing else. And so if we run the same animation, but just with a straight task queuing thing, if you're sensitive to flashing images, you might want to look away now, because that looks like this. Like, it's calling that function so many times, there's kind of no real sense of motion here. It's just, it's so fast. In fact, on this machine, it gets a task every 2,000th of a millisecond. Like, it's going to call that callback loads. So rendering can happen between tasks, yep. But you can have many, even thousands of tasks between renderings. Flashing images are gone now. Let's imagine each of these is a frame that gets displayed to the user. The render steps, they happen at the start of each frame. So we've got their style calculation, layout, and paint. It doesn't have to do each of those every time. If there's nothing to lay out, it won't do the layout steps. If there's nothing new to paint, it won't do that. But when it has to do those things, it's always at the start of the frame because it gives it as much time as possible until it needs to display the next frame, actually display the product of the work it's doing. This is nice. This is nice and neat and tidy, and I like it. Tasks, on the other hand, they do not care. They will just appear sort of anywhere they fancy. Like, the event loop ensures that the tasks happen in the right order, but in terms of timing within a frame, they don't care. And we saw this with the set timeout before. We were seeing something like this. We were seeing roughly 4 set timeout calls per frame. And that means 3/4 of them are wasted effort in terms of rendering. Some old animation libraries would do this. They're using a millisecond value. That would roughly mean 60 of them per second. They're assuming the screen is 60 hertz, but like I said, that's a fair assumption. It's not a bad assumption to make. But it eliminates a lot of that duplicate work. You'll get roughly 1 per frame. But set timeout was not made for animation. It's not scheduled properly in terms of the rest of how a frame is built. So it's a nasty hack. So due to inaccuracies, you can end up with drift, where you end up with 1 frame being missed and twice as much work being done in the next frame, which is janky and also a waste of CPU. But also, if one of your tasks runs long, it can end up getting in the way of the rest of the render steps, because it's all running on the same thread, so you're stopping paint happening when paint really wants to happen. If we use request animation frame rather than set timeout, it would look like this. Like, everything is all nice and ordered. Everything is within the timing of a frame. Even this bit of expensive JavaScript in the first frame there, it's not disturbing the rest of the flow. It's still going to be able to display a frame without skipping a frame at all. When I see performance traces of websites, this is the kind of thing I want to see, because it's making the best use of the time the machine has available. You can't avoid tasks completely, of course. Things like click events, if the user clicks somewhere, you generally want to act on that straight away. But if you have things like timers or things arriving from the network that is then going to turn into a visual update, you can just, as soon as you get your network response or your click or whatever, you can use request animation frame to schedule that work so everything kind of stays sort of nice and ordered within a frame's time budget. So I treat tasks like I treat people who drink fizzy water. Like, I acknowledge that you exist, but I keep our interactions to a minimum because I do not trust you. Do not trust you at all. I think I'm a person with empathy, but I do have limits, like anyone does. I don't get it. I've eaten a lot of stuff, some things I don't like, but I can, think, oh, I can see how someone would like that. Not soda water, it's disgusting. If anyone here drinks it, I don't think you're actually human. I think you're an imposter among us. I actually maintain a Twitter list of people I observe drinking soda water. It's not a creepy thing. I just feel like I need to keep my eye on them and make sure I know what they're up to. But when I find out the link between these people and Brexit and Donald Trump, I'm going to blow the case wide open, because there's a link there must be. And it breaks my heart to tell you this leads. This conspiracy goes straight to the top. I saw him on a plane with soda water. Every now and then someone will say to me, it's like, oh, but Jake, you drink Diet Coke, and I think you'll find the main ingredient of that is fizzy water. And I'm like, well, yeah, it's not the same. Come on, the main ingredient of air is nitrogen, right? But you would die if that's all you had. So soda water is fine if you mix something with it. It's just if you drink it on your own, not human, don't trust you. Anyway, that's request animation frame, fine. But before we move on, there's one detail of this that catches a lot of developers out, and I want to talk through it. Request animation frame up there, that comes before style calculation, layout, and paint. And this caught me out. It wasn't what I expected. Code like this, it can look sort of expensive. We're changing something, displaying it, undisplaying it, displaying it, undisplaying it. But this is actually pretty cheap. Like, JavaScript will always run to completion before rendering begins. So in this case, the browser just actually sits back and lets you have your fun changing values. It just, it doesn't care. It doesn't think about the result of any of this until the style computation steps. And then it goes, okay, what did you actually change after you ran all of that code? And there's only one bit that matters, and it's this last line here. That's all that actually changed, the very final value. And that explains a gotcha in CSS for me, or something that caught me out. I had a thing on the page and I wanted to animate it. When the user clicked a button, I wanted to animate that thing from an X position of 1,000 all the way to 500. Something that sounds pretty easy. So I had my event listener there, so on click, fair enough. Set the X position to 1,000 there, just using an inline style, fine. Told it to transition, cool, no worries. And then sent it to 500 pixels. But that animates from 0 to 500. The 1,000 pixel line, it's completely ignored. But the reason is the same as before. I'm setting the transform value twice. The first value, the start position, it's simply overwritten. The browser doesn't really think about it in terms of styling. So I figured that out anyway. So what I did was I took those other two values and I wrapped them in request animation frame. So I'm telling the browser, here's the start position, and next frame, here's the end position along with the transition sort of information. And now, it's still animated from 0 to 500, and I couldn't figure out what was going on. Well, I shall tell you what's going on. I finally figured it out by getting an engineer to explain it to me. The user clicks a button, and that queues a task. So we go and run that task. There we go. And this is where this line runs. This is where we're setting that initial transform value. So translate x, 1,000, there it goes. And then we queue a request animation frame to handle the rest. So this is where we do this bit. This is where we're setting the transition value and the sort of destination transform. But the browser doesn't think about styles until the purple block there, right? This is where the browser calculates the style changes. So again, it totally misses the first value I gave it. It hasn't thought about it in terms of styles. It's just skipped over it. And that's why if you want this to work, you need not one, but two request animation frames, one nested inside the other. And that will work. And now if you do that, it will animate from 1,000 down to 500. It ensures the browser calculates the style of that start position and then later calculates the end position as two separate steps. There is actually a hacky alternative to this. You can use something like getComputedStyle, and just by accessing that property there, I'm sort of forcing the browser to think about styles earlier than it usually naturally would. But in this case, it's, by asking it, tell me what the transform value is, it's like, oh, it changed. Oh, that's exciting. I'll actually think about that, and that becomes part of the internal model of where like objects on the page are. And as I say, you end up doubling the amount of work in terms of style calculation because it's going to have to think about it again once it gets to the render steps. But this means the animation will happen. It will animate from 1,000 to 500. The best solution for this, because this is quite hacky, the best solution is the Web Animation API, but that's something that only Chrome supports right now, so it's not really the answer right now. So if, like me, it was news to you that request animation frame is up there, it's the first thing that happens in the render steps, don't feel bad, because you might have been misled by Edge and Safari, which they get this part of the standard pretty wrong. They process request animation frame around about here. They actually do it after paint. And so it's pretty inconvenient, actually, because it means that if you do a click event or you get like a network response or something, and that's a task, and you actually want to do some painting as a result, you're going to get something painted before your code that's going to actually try and update this stuff runs. And it's going to add delay. It's going to add one frame to delay to anything you're trying to do in Edge and Safari. It's a kind of a pain if you're trying to debounce things by the display that the user's using. It doesn't really work, so it's something I kind of hope they fix. Yeah, it's not going to see your actual changes until the frame afterwards when it goes back around. Yeah, it's something I hope they fix soon, but Chrome and Firefox, they have it in the right place. It's up there before the other steps. I'm told that the Edge team have fixed it internally, so it might be in the very next release that comes out. That's enough about request animation frame, but before we continue away from rendering, I want to address a little bit of a lie that I told earlier in the talk. We're going to have a look at the compositor thread. It's something that Una mentioned in her talk. I said that an infinite loop blocks rendering, and that's kind of true, but let's have a look at this. This is it's similar to the example earlier, except that GIF has sort of got a bit of a wobble going on. I click that button, sort of roughly the same as before. I can't select text. The GIF has stopped, except that little animation is still going on. So why is this happening? Something non-standard is going on here, but it's something that all browsers do. Like, although the render steps are in charge of style calculation, layout, and paint, it isn't the thing that actually puts the pixels onto the screen. That is down to this. This is the compositor thread. It's also synchronized to the display, so it's going to go around at 60 times a second on most displays. So let's take a closer look at it. So, when it comes around to the render steps, which it skipped there because I pressed my animation too early, never mind. It's a very delicate animation, this, and I just broke it. When we get around to the render steps, to the painting thing, this is where the pixels are going to be created, but it just sends that information onto the compositor thread, and this is where compositing happens. It happens right there. And this is the bit that's in charge of getting the pixels on the screen. It's also, it's going to receive lots of different bitmap datas, and it's going to put it onto the canvas that the user sees. And this is where things like scroll position are taken into account. It's going to offset those pixels to whatever the scroll position actually is at the time. But that's not all it can do. So around here, when we get to the style calculation steps, sometimes particular styles are being set that the browser realizes, oh, hang on, like this thing that I've got to do, it's a sort of declarative animation, or it's something that I can actually move all of those instructions to the compositor and run it as a program directly on this other thread. So by declarative animation, I mean a CSS animation, a CSS transition, or a web animation, where it knows the start position, the end position up front, and the duration and the easing, everything like that. So yeah, it writes this little program and uploads it to the compositor, and there it is there. So yeah, this only works if it's the kind of animation that the compositor can handle on its own. The compositor can't draw things. It can only take bitmaps that are already drawn and move them around or transform them in some sort of way. But that works in the situation we saw before. So instead of drawing this as kind of one image, it actually ends up drawing it as two separate images. And now it can move those things around independently on the compositor. And not just position, they can be rotated. They can even have rotation in 3D. You can do particular kinds of color effects with it. Some of the hue, the filter stuff we saw before, like hue rotation, that's something the compositor can do because it's not, it's not actually creating a thing, it's just modifying a thing that's already been created. So opacity is another thing there as well. Anyway, we didn't do anything in 3D. We just put those two pieces together and gave it that little animation and then rendered that. But that is something that can happen entirely on the compositor. So, in our example, what happens when we click that button, that infinite loop? Well, it queues a task, as we saw before, and that's an infinite loop. So our event loop is stuck. It's stuck in the same way we saw before. It can't update the GIF anymore. It can't handle user interaction. But the compositor here still has those instructions. It can still go around, hit this step, apply that rotation, and composite it. And that's why we still see certain animations happening. And browsers are trying to move as much as possible to the compositor thread because it keeps those animations running smooth. So that's why particular animations aren't blocked by JavaScript. And so that's why we recommend if you animate things like transform and opacity rather than like width and height. Because when you do width and height, that triggers layout, so that has to happen on the main thread. But just moving an image around can be done on a compositor. It's super fast. OK, that's enough about rendering. We're going to take a look at microtasks. And I'd say this is the least understood part of the event loop, and it's also sort of one of the newer parts of it. I associate microtasks with promises. This is where I've encountered them the most. But it isn't where they started. It isn't where they originated. Back in the 1990s, browsers wanted to give developers a way to monitor DOM changes, to sort of observe what is actually happening on the page. The W3C, they gave us mutation events. So you could just add a listener like this, DOM node inserted, and this event will fire when something is inserted into the DOM. And there was lots of other events as well. Good idea, but the implementation was problematic. So if we take a look at this piece of code, so here I'm adding 100 span elements to the body, and I've given them some text as well. It just says hello. Fine. How many events would you expect to receive? How many node inserted events would you expect to receive for this piece of code? 1 for the whole operation? Nope. 100, so 101 for each span. And that's not all. You get another 100 for each bit of text being inserted into each span. So that's 200 events all in all, and that's because the events bubble. Yeah, and it turned out to be pretty bad, because if you were doing just like a little bit of work in one of those event listeners, it could be being run 1,000 times for a relatively trivial DOM change. And so a little bit of work would suddenly become a performance disaster. What we really wanted is a way to sort of to tell developers stuff has changed, but we wanted to be able to batch that together so it wasn't calling the same piece of code over and over again. Earlier we saw what browsers do with style changes, where it just lets you change your styles and whatever. It kind of holds back until the render steps and then goes, oh, stuff has changed. We wanted something similar here, but for DOM nodes. The answer became mutation observers rather than mutation listeners. And they created a new task, like a new sort of a new queue called the microtask queue. Most documentation I read on microtasks, it says like they happen after a task, which is true. Yeah, just over on the left there, just after where a task is, there's microtasks. But that's not where you're going to encounter them. That's not only where they happen. It's not where you're most commonly going to see them. Microtasks happen whenever JavaScript has finished doing some stuff. Meaning like the JavaScript stack has gone from having things in it to having nothing in it. And that's where you'll encounter them. So you can end up running microtasks during a task, during the render steps even, pretty much anywhere you can run JavaScript. And that means like, so this piece of JavaScript here that will run to completion because there's stuff on the stack, adding 100 spans, adding the content, and once JavaScript is finished executing, the stack empties. In your mutation observer, it will give you a callback for that, just one. And it'll tell you all the changes. Promises, they also use microtasks. So here we queue a microtask to handle this callback inside there. We log yo. Now our script is done, so the JavaScript stack is empty. We process the microtasks, and we log hey. So it's that way around. And that means when a promise callback is executing, you're guaranteed that no other JavaScript is midway through at the time. And that's a kind of important guarantee that it gives you. The promise callback is always at the bottom of the stack. But what happens if we create a loop using microtasks, similar to the other examples we've had, similar to the set timeout one, but using microtasks rather than tasks? Well, same test as before. Press the button, and everything locks up. It blocks rendering just like a plain while loop did. So sure, like, promise callbacks, they're async, but what does async actually mean? What do people mean by the term async? All it means is that it happens after things we call not async. You know, it's going to happen after things we call synchronous. It doesn't mean it must yield to rendering. It doesn't mean it must yield to any particular part of the event loop. It only means that hey is going to come after yo, which is going to execute synchronously. We've looked at 3 different queues so far. We looked at tasks, we looked at animation callbacks for request animation frame, and now we're looking at microtasks. And just to make your lives easier, they all empty in a slightly different way. Like we've already seen, like when there's a task, when we take a task off the stack, we just take one. Only one task per turn around the event loop. And if another task is queued, it goes on to the end of the queue. When it comes to animation callbacks, when we get around to that part of the event loop, it will take all of the items that are in the queue, except ones that are added while we're processing that queue. Those are left until the next frame. That's how animations work. Microtasks, on the other hand, they are processed until completion, including items that are added during processing. So if you're adding items as quickly as you're processing them, you are processing microtasks forever. Like, the event loop can't continue until that queue is fully emptied, and that is why it blocks rendering. I get really excited about this stuff. Diving into this spec, I find it really interesting. It really sort of taught me about all of the sort of problems I'd had in JavaScript, all of the sort of weird timing things I'd found, and just didn't have an explanation for earlier. Something I really enjoyed doing. I used to have a proper job, like many of you do. This stuff like the sort of making the animations, looking at standards, writing standards. This was my hobby, but then my hobby became my job, and now I have no hobbies. I unexpectedly became a boring person. And I genuinely didn't notice when this happened. The first time I became aware of it is I went for an eye test. And just sort of making small talk, the optician said, you know, and what are your hobbies? And that's what I was like, oh shit. When did this happen? And like I say, I'm a nervous person, so the silence was, it felt like it had lasted 3 years, even though it was only a couple of seconds. So I thought, well, I can't say nothing. I can't just say movies. Everyone says movies. I've got to think of something. And I shit you not, I panicked and I said, I play the piano. I don't play the piano. I don't know how to play the piano. And then I started stressing out that she was going to say, like, oh, well, that's good. Let's take away the letters chart. Let's have some sheet music. What chord is this? What song is this? Play me the next bar. Thankfully, that didn't happen, but I am actually afraid to go to the opticians now. I haven't been back just because I'm afraid there's going to be some serious in-depth piano chat out of nowhere, and it's all my fault. I don't know why I go out sometimes. Okay, I think you're ready for this next one. I occasionally run little JavaScript quizzes. Maybe that's my hobby. Nope, that's my job as well. Fuck. This is one of my favorite questions, though. I really enjoy this one. We've got an event listener here. There it is. We've got a microtask there. It's going to log microtask 1, and then we've just got synchronous listener 1 there. But we have another listener on the same element doing exactly the same thing. The question is, if the user clicks the button, what happens? Which order are things logged? Well, our first listener is going to execute, so that's on the stack. We've got a listener 1 on the JavaScript stack there. That's fine. That's going to queue this microtask here, so we'll add that to our list there. And then we're going to log listener 1, fine, so that becomes our first answer, listener 1, no problem. Most folks agree on this bit, but what happens next? A few months ago I ran a Twitter poll about this question, and 63% of people say the next one is going to be listener 2. 5% of people think it's just going to be nan, 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 then infinity, fair enough. But 63% of people think it's listener 2. It's neither of those, but if you think it's listener 2, then you're in good company. It's a really tricky edge case. It's what most people think. But no, our listener has finished at this point. So we've gone from having something on the JavaScript stack there to having nothing on the JavaScript stack. So that means it's time to process the microtasks. So we go up there, and this is where we log microtask 1. And that's done. We've processed our microtask queue. And that means we're on to the next task. We can go through this next callback, and the same happens again. So listener 1, microtask 1, listener 2, microtask 2. That's if the user clicks the button. What if the button is clicked with JavaScript? Yes, it does make a difference. For starters, our script is on the stack, where we call click, and that synchronously dispatches the event. So that's going to be on our JavaScript stack from the start. So we're going to have our first listener, fine. We're going to queue a microtask there as we did before, so we'll add that to the list. And then we're going to log listener 1, so the first thing happens there. And this is where we were running microtasks before, but we can't run microtasks this time because our stack is not empty. Our call to button.click has not returned yet because these listeners, they're dispatched synchronously. So we need to go on to the next listener. And here we queue another microtask, and we log listener 2. And now we have finished both the listeners. The call to button.click can return. The script is off the stack, and then the microtasks can happen. So just that small change to code actually changes the order that these things happen. If you run automated tests, maybe watch out for this one. If you're clicking buttons using JavaScript, it's much better to use something like Chrome DevTools protocol, where you can actually do mouse events that don't run synchronously. They run exactly the same as if the user presses the button. Or you can try and find something that will do the clicks at the operating system level. This issue also came up while we were looking at how to bring observables to the DOM and how they were going to integrate with promises. And we hit this question. So if we're going to use like a sort of promise-based thing to provide events, is this going to work? Like if we've got a promise for the next click on an element, can the user then, the developer then do a dot then and prevent the default from happening? Like promises are async, so is this too late? Turns out it's not too late. Promises are async, fine, but it turns out it's not going to be a problem at all. But same again, unless the link is clicked with JavaScript, and that just changes the shape of everything. And to figure out why this happens, we need to kind of take a look at the spec for clicking a link. This is a very simplified version of it. So we create an event object because we're going to be firing event listeners, and then for each callback of the event listeners of type click, we'll invoke that callback. So we're calling through all of those listeners. And then we go and have a look at the object and go, has the cancelled flag of this event object been set? If it hasn't, follow the link, otherwise don't. And this cancelled flag happens when you call prevent default. So we're kind of querying there. Did one of those listeners call prevent default? So in this example, if the user clicks the button, the microtask is going to happen here because that JavaScript stack is going to have stuff in it and empty out between each listener. So this works fine. Event default is called, and it's going to be, that code's going to run before step 3 there. But if click's called, that's going to be on the JavaScript stack for that whole thing. So we can't run microtasks there. They actually run sometime much later when the rest of the script has finished. So all of a sudden, just if a small change there, prevent default isn't going to work. And so we're kind of wrestling with the spec on that of thinking, is there a way that we can avoid this being an issue? Is there something that we need to change there? Right. How long will I get away with speaking for? Someone give me a hand gesture. What do you think? 2, 3 minutes? All right. Well, maybe. Harry's saying 5. Well, I'll just carry on then. I wanted to talk about event loops. Now, I know what you might be thinking. What have we been talking about for the past 45 minutes? Well, we've been talking about an event loop. But in reality, modern browsers have many, all doing their own independent thing. For instance, if you create any kind of worker, it gets its own event loop. That's how it doesn't jank the page. The browser UI normally runs in a different event loop, and sometimes multiple pages will run in their own event loop. I actually really love this slide. I can't leave it on for too long, else the laptop will melt through the table, but that's fine. So which pages run on the same event loop and which ones don't? There is no straightforward answer to this. It's a tough one. For instance, here's an old version of Firefox with the same test as before, but this is 2 different sites. But although I've locked up one tab, this other tab has become locked up as well. In fact, the whole browser has become locked up. This is because Firefox uses one event loop for the whole browser, or it did until November, I think, is when they actually changed things. So the way around this is they would eventually halt JavaScript from running. But all of those things that were still queued up all kind of happen at once, and you might have seen warnings like this. Whereas this is Chrome. I've locked up one tab, but the other tab's still working, and the browser UI still works. And this is because it's all running on separate loops. Chrome did this in version 1. IE8 did it in some cases. Edge does a good job. Safari 7 introduced it. Firefox introduced it in Firefox 57 in November. It was the last to do it. All down to their extension system. They couldn't change because of extensions people depended on. There's only one rule in the spec that says when things must share the same event loop, and that's when 2 windows have synchronous access to each other. So that's in this case, I have an iframe. I can reach into that iframe, and I can get hold of the document. I can append stuff to it because it's same origin. So that means because I've got synchronous scripting access, it must be on the same. It must be a part of the same sort of group that run in the same process. Whereas if it's another origin, we do this, and it gives me a security error. So I don't have synchronous access there, and that means I can't mess around with the contents of your bank or your email or something, which is a good thing. But it also means it can run on a different event loop, and the 2 processes can remain separate. And that's very important with the sort of Spectre and Meltdown bugs that we've seen recently. So the one case where this is a bit weird is if I've got a couple of links here. I'm going to click this one, new tab, 2 pages, same site. Here I click this one, it blocks the other tab there. And the reason for this is although it's opening a blank tab, it feels like, well, there's no scripting access between them, but there is. The new page actually gets window.opener, which is scripting access to the other page. So that's why it has to it's the same as iframes before, it has to run in the same event loop. It can be different, so another link just to the same page again. This time, it just blocks one tab. The only difference between the 2 there is rel equals no opener. A little trick that not many people have heard of, but it means it just stops opener being a thing in the other tab. It's really good for security. I would do this on all external links, but it also is good for performance there as well. So, I should probably leave. I've been kind of taking too much time on the stage. So, I was going to talk about a security thing, but it's not really that important. It's not that exciting. All of this stuff is stuff that's just helped me sort of understand, whereas usually I would end up wrapping like something in a set timeout call because it was happening in the wrong order, or like I would end up just like, and even with the set timeout, I was ending up putting like a value there, 16, that's not working, let's try 20, or that's sometimes working. But actually knowing the order of things, knowing the stuff about the event loop, I no longer have to do that anymore. And I hope that's helped cases where you no longer have to do that anymore. Like I said, I'm a stressful person, so I'm going to go and collapse in a pile now. You've been a great audience. Thank you very much.